Welcome back. In this session, we'll talk about experimenting with technology. Now, there are lots of ways of using technology to help you experiment. You can connect sensors to your computer to automatically collect data. You can enter data and graph it. But in this session, we'll focus on a special kind of experimenting with technology, simulation. Now, simulations are really important, much more today and in the future than in the past, and we'll see why. Simulations are certainly actively used by adults in training for the workplace and other things. For example, if you want to learn to fly a plane, you use a flight simulator. To drive a car, a driving simulator. To practice medicine, there are all sorts of simulators on mannequins and on computer games that you learn to practice the skills so you might injure an avatar in a game rather than a real person. The same applies for military training. Simulations are everywhere in the real world. In science, simulations have a special role because simulations have become really a third kind of science added to experimental science and theoretical science. So, for example, something is too large or too small to actually experiment with in a lab, like a galaxy or a molecule or a cell. Something that happens too fast or too slowly, such as a nuclear reaction or evolution, something that's too dangerous, fission, the spread of a virus, something that happened in the past or will happen in the future, like evolution in the past or climate change in the future. So this new kind of science is called computational science because it uses the data that are created by models, such as simulations, and works on that. If the model is run into the future, it's used for predictions, such as weather forecasts. Now, simulations have been used by kids and in schools for decades. In the background is SimCity, which has been a mainstay of kids learning to plan for probably 20 years. And it captures the essence of simulations so that a student would use variables, would modify the variables in creating the city, figuring out where to put residences, where to put parks, where to put businesses. Similarly, they need to create adequate road systems with enough capacity. To do that, the mayor has to raise taxes, not too high or people will leave the city. Too low and you can't get enough first responders, firemen and policemen, to take care of disasters such as this tornado or a crime wave or a fire. So in creating the city, by manipulating the variables, students discover the relationship between taxes and services, the relationship between a balance of residents and business. They see cause and effect. Too little taxes, not enough first responders, disasters destroy the city. This is an example of a complex environment with multiple interacting variables that are so complicated you can't accurately predict the outcome just by knowing the initial conditions. You have to run it through and have the variables interact. We call that emergence, and this is something that's part of every environmental science, weather science, evolution, climate change. They're super powerful concepts. Other simulations that are used in schools, well, the old Oregon Trail's been around forever, but there are social studies simulations like Oregon Trail. Here's Civilization, a famous simulation where you start with a village. Maybe in this case the village would invest in fishing, create nets with their which was a new technology at the time. Maybe this would grow into a fishing port, and then maybe a transport hub as the city grows. There are dedicated simulations for special parts of history, such as ancient Rome here. And in the sciences, you may have heard of the game Portal. It's a commercial success, lots of fun to play, but it's based upon accurate physics principles of like the reflection of light, gravity, mechanics, so kids can not only learn and practice physics concepts with this game, they can have a lot of fun. Well, we're going to explore the PhET simulations created at the University of Colorado at Boulder. They have about 100 simulations aimed mostly at K-12. About 50 of them for elementary, a few more for middle, a few more for high school, a few for university. And as you can see here, we have a population study. So we have predators, foxes, prey, rabbits, and we have some variables. So if we put this in the Arctic, the rabbits with white fur would probably survive better than rabbits with brown fur. So we can graph the success of the various genetic traits of the predators and the prey. We could add a mutation, add brown fur, and see how that changes as we run the simulation. And we can edit the genes to figure out how this process works. Studying it in real life would simply take too long, but a simulation like this can run in a few minutes. We can change the variables, run it again, and so on. In other areas of science, here's a PhET simulation where you can see the electrons moving in a wire, and if the circuit is set up correctly, the light bulb lights. So next we're going to visit the PhET site. You'll see how the site works and how some of the kind of cool simulations operate. Okay, here we are at the PhET site, and you can see at the top left the URL is simply phet.colorado.edu, and you see a variety of their animated simulations. But the way to work with any of these is to start by clicking the big button in the middle, Play with Simulations. To see the roughly 100 different simulations in PhET, we can zoom in on the categories: physics, bio, chem, earth science, math, or by grade level. So we can see elementary, there are about 50 that we could select from. But let's take a look at physics, because there's one that I want to show you in particular. So here are all the physics simulations, and you'll notice there's a little badge in the lower right hand of each simulation icon. One has a big number 5. That means it works using HTML5. That means it would work on an iPad or an Android tablet. The others won't. Those that have a coffee cup with the aroma coming out are Java applets, so you need to have an up-to-date Java implementation. Those with a big letter F run on Flash. But the one that we're going to see is Energy Skate Park Basics, and I already have that loaded so we can see what that's like. So if we're just learning this, we can click the intro and we can see kind of how this works, and we put a skater up here, and okay, that's how it works. Then we can add friction to the model with our slider here, or go to a playground where we can create our own energy skate, kind of a coaster. So let's see how this works. Let's say that I wanted to create something other than just that simple up and down. How about a camel's hump? So you see that just by using the sections provided here, we can create a camel's hump. I'm going to turn friction off because it's a little easier. I'm going to grab our skater, and let's see if that worked. Okay, that's pretty cool. So away he goes. Now he's tied into there. I'm going to get him. Oh no! So we can make this a little more realistic by keeping him from sailing over quite so seriously. Let's try it again. Up there, and this time, okay, I did it nicely. Now we can really extend this. So this is something that like a fourth grader would go crazy over, especially if you show them something like this. You see, we can actually make a loop-the-loop. And if we just kind of work away on this, let's see how this works. Okay. And let's get these ends up a little higher, and let's see if he survives or if he falls. Okay, away you go. All right. So you can see that kids would love to explore this stuff for fun, but then you can, what is it showing scientifically? Well, you can click the graph to show the active changes in kinetic and potential energy, thermal energy if you turn on friction. We can see a pie chart following him as his energy changes depending on his position and his velocity. And you can see how that velocity changes, how it goes to zero, where it's the fastest, and so on. So it allows you to scientifically explore a concept, in this case of motion. You can slow it down. It's a cool system. Let's take a look at another simulation. This is an Equationgrapher. Initially, it looks like the most boring thing in the world, and the equation, the line, the graph, is this red line. Okay, and we're using this this formula up here, y equals ax squared plus bx plus c, which many of you probably did not like when you first learned it, because it's abstract. It's too hard to learn. Let's see how in about 30 seconds you can understand what the pieces do. So the C tells you simply how high the graph will be. The A for x squared just tells you its curvature. How tight a smile will it be? How deep a frown will it be? And the B simply tells you the slope of the whole graph. That's all there is to the x squared plus ax squared plus bx plus c form. So let's see how we can do this. Let's say we have these this 0.07 x squared plus 0.42x, so on. Let's see how we can see the components. There's the A component. There's the B component. You can see how it's tilted. There's the C component. You see how it's lowered. That's all there is to second order equation graphing for a parabola. It's awesome. Let's take a look at a way that younger kids can explore graphing lines. So when they're introduced to slope, here's an introduction which gives them the basics and they can play with it. Then they get slope intercept and then point slope, and finally, once they've been introduced to those ideas, they get to practice it in a game that has up to 6 levels. So it can start with just set the y-intercept. That's pretty simple. And then it can go all the way to something like this, where there's a much more complex line to graph. And it's a way that kids can learn by experimenting, by trying, getting feedback from their errors, and learning in a very powerful visual way. So I hope you enjoy your experiences with PhET. Bye for now.